face field modeling of fracture and its application to hydrogen embrittlement. Before I start, I should say that my postdocs, experimental postdocs and PhD students always complain that I don't say anything about our experimental capabilities. Well, in this area of hydrogen embrittlement, not only we work from the computational side of things, but we also, as you can see here, have established a lab that can do almost every type of test. Now we are in the process of installing hydrogen gas charging, so I think we have everything in place. This is, of course, in addition to the usual microscopy and fracture and mechanical testing facilities. And as you know, the UK is now not part of the European Union, but part of the Horizon Europe and all the European Union funding programs. So we're always open to establishing collaborations and with working with you in any program that you see of interest. Anyway, let me get into the business. So what is this phase field that people keep talking about? I had this slide prepared for a workshop that I had to give some years ago. I think it was in 2021, and I didn't have time to update it, but I can promise you that the trend continues to go in the same direction. So what you see here is basically the number of articles or number of papers that have been published as taken from Google Scholar every year with the words phase field and fracture. 2010 was the year where phase field took a big jump thanks to some solution schemes that Christian Mie developed. And you can see that it's growing almost exponentially since then. And it's really remarkable how popular these methods have been. I think last time I checked, more than a third of all computational fracture papers were made with these phase field fracture methods. And I was last week in ECOMAS in Lisbon, and there were, I think, absolutely every day, at least 3-4 sessions on phase field fracture. So it was by far, at a conference of close to 3,000 people, the most widely used numerical technique. So there seems to be a big boom happening in here. So let me tell you a little bit of why this is so successful and why I think it was continued to be like this. So this slide summarizes a little bit of why this is success. So here you see experiments and computer simulations of multiple cracking problems across a wide variety of materials. You see metals, ceramics, rocks, composites, glass, even functionally graded materials. Some results are from our group, some are from other groups from the literature. But in general, what you see here is basically two things. One is that no matter how complex your fracture problem is, the method is able to capture. You can see here, if you look, for example, at this problem, you can see crack branching, nucleation of secondary cracks, crack kinking, coalescence of multiple cracks. So very complicated fracture phenomena. The method has no problem in capturing this. And then the other aspect that you see is that these predictions, these complicated fracture patterns seem to be in a remarkable agreement with experiments. So I think this is the two aspects that I'm going to be emphasizing throughout this talk. I think the method is very powerful and the method is very popular for two reasons. One is that it's computationally very compelling. It can handle problems of arbitrary complexity. And the second one is that it's physically very sound. It's based on the thermodynamics of fracture, so it's based on well-established fracture mechanics theory. And myself, I consider myself a computational fracture mechanics person. I work with, I think, absolutely every method out there. I started with some remeshing, then I moved to XFEM, then I moved to quiz-Ipsum models. And I enjoyed my time using these methods, but when I came across phase field modeling, it has been really a blessing. It's a complete game changer for us. So I'm happy to tell you about this wonderful adventure that has been to come across these phase field methods. So let me tell you a little bit of, again, these two strengths. Why is it computationally more compelling than any other method, and why is it physically more sound than any other method? So first, the computational side of things, I would just say that just to provide a bit of concept, what is this idea of phase field? The idea is actually very simple. So whenever you have an interface or two faces, it could be crack material points and crack material points. Then you can describe that interface as sharp and discontinuous. This is the way you'll do with maybe a quiz-Ipsum model. But then what phase field does instead is to smear that interface over a finite domain and use this phase field as an auxiliary variable to describe where the interface lies. And this kind of implicit representation of interfaces of cracks through this variable, this auxiliary variable, this phase field variable, is computationally very compelling, because then you just need to define a differential equation for the evolution of the phase field, and then you're able to capture interfacial problems of arbitrary complexity. So there's three key advantages that I always like to emphasize. One is that the interface equation is defined in the entire domain, so there's no need for any special treatment. The second one is that topological changes, such as divisions of merging of interfaces, can be naturally captured without any ad hoc criteria. So you can have crack branching, coalescence, all of that comes for free. And a third one that is, of course, very convenient to us is that it's very well suited for multi-physics problems like hydrogen embrittlement, because you can easily combine this interface equation with equations describing other physical phenomena. And well, phase field modeling has been a revolution in many areas of science and engineering. It all started in the condensed matter physics community, which is now by far the most widely used technique to simulate solidification and macrostructural evolution. Today, I'm going to be talking about this application to fracture mechanics, when again, as I said before, is really taking off as the dominant tool in this area. And recently, we have also shown that it can be a game changer in corrosion, because you can use the phase field to evaluate the evolution of the corrosion front. So basically, I guess the summary or the takeaway is that it's a very powerful computational technique to simulate the evolution of interfaces. Those interfaces could be microstructures evolving, could be cracks evolving, or could be corrosion fronts evolving. Today, I'm going to focus on this one, and you can see, again, this is the outcome of a simulation. You can see why it's so popular. This is hydraulic fracture, I think. That's why you see so complicated cracking patterns. And again, you see those very problematic cracking patterns, very complex cracking patterns like crack branching, coalescence, initiation of secondary cracks, all being naturally captured in this framework. But I think that the point that I want to emphasize more today is more the physics, because yeah, it's very nice to have a tool that allows you to get nice colors, but if those nice colors do not correspond to reality, then you have a problem. So why is it? Well, let me tell you about the table of contents, but I guess the question is, why is it so physically sound? And this is going to be my first part of my talk. So I'm going to spend some time explaining why facial fracture and also fatigue predictions are physically sound. So I'm going to explain a little bit about the underlying theory, and then I will explain how it's well connected to fracture mechanics understanding. Then I will discuss quite briefly a bit the numerical implementation and explain for those of you working on this area why it's numerically so robust, why it's so compelling. Finally, I will move to some representative results in the context of hydrogen embrittlement. I will show how the model allows us to deliver some unprecedented degree of agreement with laboratory experiments. And then finally, since the focus here is on pipelines, I'll have a case study where we show that the method can be used to understand at what pressures we can transport hydrogen in existing natural gas pipeline infrastructure. And I think this is important because there's many problems, like the pipeline problem, where using computational methods can be critical, because it's very difficult for us to evaluate in a lab whether we can transport hydrogen on natural gas pipelines or not, because we know that the problem are wells. Wells have residual stresses. It's very difficult to obtain standardized samples from heat-affected zones. Wells can be of very different types. Pipelines that have been there for decades can have very different distributions of defects. You have very different types of pipelines and very different types of grades of steels and wells. So there's many scenarios that you need to evaluate. The scenarios that are complicated, how do you introduce the residual stress in your model, in your experiments. And here's where I think a physically sound model can make a big difference. So let me tell you how we can use this model to determine, what is the hydrogen purity, what is the hydrogen pressure that will allow us that we can transport through those pipes. So let me start with the first part. Okay, why is facial fracture and fatigue predictions physically sound? And I'm going to assume that everyone here has some understanding of fracture mechanics, but if not, please don't hesitate to interrupt me. I'll be happy to elaborate a bit more. So I think that one of the strengths or one key strength of the method is that it actually provides a platform for Griffith's energy balance. So everything is well based on the thermodynamics of fracture. And, Griffith was the father of fracture mechanics, and he postulated this energy balance that, became what we then later use for stress intensity factors, following the work of Irwin and so on and so forth. So this is the foundation of the field. Right? And the foundation basically is that nothing but an energy balance resulting from thermodynamics. So Griffith said, in order for a crack to grow, the energy stored in the material due to mechanical straining has to be equal or larger than the fracture energy, the energy required to create tunnel surfaces. So this is a very simple energy balance, but it has to be fulfilled. So this is often what we call the critical energy release rate, or toughness, or fracture energy. And then we know that if we are able to express this mathematically using a variational approach, then we can define a functional. And if we're able to minimize this functional, then we're able to predict the evolution of cracks based as an exchange between store energy and fracture energy. So based purely on Griffith. And this is quite challenging. And this is the reason why we decided to convert J, energy release rate, to stress intensity factor and move ahead with the stress intensity factor approaches, even though they are equivalent, is because of the reason that it's very difficult to solve a system like this. But phase field gives you an opportunity to do so, because phase field is a little bit like a marker. So it tells you where the crack is. You can see here, it's a variable that takes, similar to a damage variable, right? It takes a value of 0 in intact material points. It takes a value of 1 in fully cracked material points, and it's interpolated in between. And similar to a damage variable, of course, it will degrade the load carrying capacity of the solid. So if your phase field is equal to 1 in fully cracked material points, you have no load bearing capacity. And then importantly, from the numerics perspective, you have a length scale, but also from the physical perspective, I'll discuss that later. You have a length scale because you have a gradient here, which means that your results are going to be mesh independent. And this is very different to every other local damage model, like a Gurson model, where if you change a mesh, you get a different result. And this is important because, of course, our industrial partners, they tell us, we don't want one engineer to get one result and the engineering setting next to him. We want all engineers to get the same result, right? So we need a mesh independent method. And you can get a good overview of the method just by looking at the balance equations here. So the top one is the balance of linear momentum, the usual equation that we solve when we're interested in the deformation of a material. And you can see, of course, that the phase field degrades that load carrying capacity. And then you have an equation for the evolution of the phase field. This is the only thing that is extra to your usual finite element code. And everything here is a constant, except for this guy, the strain energy density, which, as we know, is the energy stored in the material and increases with mechanical straining. And then, of course, as you can see, basically, this is a competition between this strain energy density, the energy stored in your material, and the fracture energy, a material property, toughness, that we can measure easily in our lab. So what you see here, by the way, is a crack branching due to the application of a dynamic load. So the point that I want to make is that you can capture very complex cracking phenomena just by solving these additional differential equations. And as I will show you later, you can do that on the original finite element mesh and in a very robust fashion, so without any convergence problems. And by the way, let me emphasize that following what is typical in the phase field community, I'm going to use red color to denote cracks and blue color to denote intact material. So whenever you see red things happening, those are cracks. So, okay. Well, we said that mathematically this is based on Griffith's energy balance, so it should be well in agreement with fracture mechanics. And we know that mathematicians have shown that there's something called gamma convergence, that is actually the case, that in principle, this will give you the same results as if you could able to solve Griffith's equation and if you're able to use fracture mechanics. But let's do a test, right? We didn't believe necessarily in mathematicians, so we said let's do a computational test just to make sure that in practice this is the case. And the first question that we wanted to answer, does the method predict that cracking starts whenever your energy release rate is equal to your material toughness? Or in other words, the relationship between energy release rate and the stress intensity factor. Does the method predict that cracks will initiate whenever your fracture toughness, whenever your stress intensity factor is equal to your fracture toughness? And one way of doing this is by using what is called a bounded layer model. So this is a model where you prescribe, using Williams solution, elastic solution, a displacement field in the outer boundary as a function of your stress intensity factor. So then for a given stress intensity factor what is the displacement field, and then you see with your phase field whenever the crack grows. So you start increasing your K, and then you see at what time the crack grows. So you're measuring your G, your K, and then you see when the crack propagates. And this is what we get out of the experiments, out of the numerical experiments. So fracture mechanics tells us that cracking should start when G equals GC, or K equals the toughness and fracture toughness of the material. So failure should start at 1. And we see that initially, if you use, this is the length scale of the phase field, this is the element size. So if your mesh is very coarse, then you overshoot. But as your mesh becomes fine enough, then you converge to the right result. So this is good news. I mean, it confirms what the mathematicians predicted. Phase field is able to predict the initiation of cracks at the right time in agreement with fracture mechanics. And the only thing that was telling us is, careful, make sure that your mesh is sufficiently fine. In particular, it seems that you need 7-8 elements to resolve your length scale. But that's easy because we know what is the value of this guy. So we just need to pick our finite element mesh 8 times thinner than that. So this seems to be good news. We were also interested in knowing if cracks grow fulfilling this kind of energy balance, because that's also something that fracture mechanics tells us. And for that, we look at a double cantilever beam. And if you look at a double cantilever beam, you can use beam theory to get an expression for the energy release rate as a function of elastic properties, curvature, beam deflection, and so on. I won't get into the details, but yeah, It's straightforward to use beam theory to get an expression for G. And then we did our numerical calculations, and we saw the crack growing in this beam, and we saw that these are two types of phase field models, but we saw that we were, in both cases, very close to the beam theory solution. So things seem to be going well. It seems to, as I guess mathematicians expected, the numerics confirm that we are able to predict how cracks evolve, how cracks initiate at the right time, and how cracks evolve at the right time in agreement with stress intensity factor and energy release rates. So that's good. But that's not the only thing that we care, because we know that Griffiths and fracture mechanics, they are applicable to situations where we have large cracks. But we also know that engineers normally, when they are looking at cracks, and this is, for example, something you do in the nuclear codes, all the R6 and all these nuclear codes, what they will say is, they will measure the crack size, maybe with non-destructive evaluation techniques, and they will say, if my crack is very small, below what they call the transition flow size, which is when you get the intersection between the failure stress predicted by fracture mechanics and the failure stress predicted by the material strength. If it's below the transition flow size, the standards will say you use plastic collapse or some sort of a strength-driven failure mechanism. If it's larger, you use fracture mechanics. So we have seen that phase field agrees very well in this area, but I was wondering, can I use my phase field as well also for situations where my cracks are very small, where maybe fracture mechanics does not dominate? This is a situation where you have a strength-driven failures or plastic collapse. And the good news is that you can see here the outcome of a 1D simulation, or if you take one element and you do that simulation with phase field, you see that you get a response, a stress-strain response like this. So this is basically, this resembles a traction separation law for those of you working with cohesive elements. And basically you can get a closed form expression that relates the material strength with that length scale that I showed you before. So the model takes as input two parameters. The fracture energy, you saw it in the equation here, right? This is the equation that you're solving. The only two parameters that you have, this is strain energy density. You know how to calculate that from strains. The only two, this is what you're solving for, the phase field. And the only two parameters that you have are the length scale and the fracture energy. So the fracture energy, we know, we can measure, and is, you can correlate with fracture toughness. And the length scale, as you can show here, determines the material strength. So the two parameters that we have into our model, they have a very clear physical meaning, because one is strength and the other one is fracture energy or fracture toughness. So this is, I think, good news, because not only means that all the parameters in the model, first of all, we only have two parameters in the model. This is very different from any other model. If you think of Gaussian models have 8, 9 parameters, 2 parameters, both of them with a very clear meaning, and both of them can be independently measured in your lab. So strength and toughness. And this is, again, good news, not only because is able to capture, it shows that the model not only is able to capture the Griffith type of approach at a very large crack sizes, but it's also able to capture strength-dominated failures. And this is good news, because if we are able, and you can see that it also naturally transitions in between. And this is very good news, because it means that not only we can deal with large cracks, but also with no cracks or very small cracks, which means that everything in between is doable. We can deal with the two extremes, and we can deal with everything in between. So no matter what is the crack size, what matters the dimension of your crack, the model is going to give you the right physical result. And of course, this is what we see from experiments. So here you see experimental data from various materials. Again, fracture stress versus crack length, and you can see this kind of behavior. So if you run the simulations with phase field, you're going to get exactly the same behavior. You can see it here in a qualitative fashion. So this is good news. Not only is in well agreement with well-established fracture mechanics theory, which is what underpins some standards, but it also is in agreement with this kind of toughness versus strength-dominated failures, which also underpins our engineering standards. So that's great. And it also means that, again, the two parameters of the model, they have a clear physical meaning, because we're talking about strength and toughness. Okay, let me show you actually how the model works. And this is something that we did recently. This was Purdue and Sandia in the US. They decided to do what they call a damage mechanics challenge. So this was what some people call the blind Robin test. So they said, we're going to 3D print some material, some sort of rock or gypsum, I think it was. They didn't tell us what material. They said, we're going to 3D print a material. We are going to give you some data of the material, a uniaxial compression test, a Brazilian test, and a 3-point bending test. And now we're going to ask you to predict the failure of that material under more complicated scenarios. So particularly, they're interested in various 3-point bending configurations, but non-standard 3-point bending configurations where they would, tilt the crack and do funny things. And again, it was a blind test. They did not provide the data for these funny configurations. They just provide a simple 3-point bending test, Brazilian test and uniaxial compression test. And they say, we give you this data. We don't tell you which material is this. It was a 3D printed rock. You guys use your models and tell us what to do. And a lot of people from all over the world contributed and with different models. And we decided to do so with phase field. Let me tell you a little bit how the story went. So first of all, this is, we were asked to simulate those 3-point bending experiments. There was one of them that was given to us in advance, so we used that for calibration because, as I said before, the only 2 parameters of the model, well, the 4 is, Young's modulus, Poisson ratio. We knew these 2, or more or less. I mean, on Young's modulus, otherwise you can fit to the linear part. And then we have toughness and failure stress, so we can calibrate the failure strength and the toughness to one experiment. They also give you a Brazilian test, so in principle you have your strength. We can calibrate that to an experiment. And then this is the predictions that we got. This is predictions that we got in terms of crack trajectory, depending on where the crack was aligned, a 3-point bending test. And these were predictions that we got in terms of force displacement response. We send it over to them, and then when everyone sent their calculations, they release the data, and the data was released relatively recently. As you say, all of it is explained in a paper that we just published in Engineering Fracture Mechanics. There's a special issue dedicated to this challenge. They released all the data, and this is how the data look like. So these are 3 replicate experiments, and as you can see, this is the force displacement curves. We were in quite good agreement, I would argue, across the board. So this was good news for us. I think this is the experiment that was used for calibration, and these are all predictions, and as you can see, a very good agreement. And then they released the data of the crack trajectories, and I don't know if you can see it clearly, but again, it seems to deliver a very good agreement. And in fact, we can superpose them. And this is the computational and the experimental results superposed. And as you can see, and again, this is a blind agreement. When you have a parameter that has a model that has 10 parameters and someone gives you an experiment, it's very easy to calibrate and to get a remarkable agreement with that experiment, because at the end, you need to fit one curve and you have 10 parameters. There is was a Newman who said you could fit an elephant with 3 parameters. So it's not too difficult. But when you do it blindly, that's a different story. So this data was not available to us. And then they also released data they asked for data for a 3D case, because they have good microscopy or XCT facilities, so they were able to measure the crack surface. So they say, oh, could you run a simulation in 3D and tell us, whether you get the right crack surface? And this is what you did. And this is the result of so this is their XCT image. Then they send us a MATLAB reconstruction of the XCT image, and this is the finite element prediction. So it seems that even when you look at the crack surface in 3D, the model is able to give you that good agreement. So okay, that closes this part. We have a model that has as input only 2 parameters, the material strength and the toughness. So that's good news, because we know what are the toughness and material strength of most of the materials that we're interested in. And if we don't know, we know how to get that out of a test. And the model seems to, be in agreement in well-established fracture mechanic theory, which is good because it means that it follows our engineering standards. But it's also good because it means that, there's a reason why fracture mechanics is so well-established. It delivers a very good agreement with experiments. And I think these kind of blind tests are the ultimate test to these kind of models, and it seems to have worked very well. Okay, so far I haven't discussed anything about plasticity. And a question that I often get is people say, oh, but Griffith, when he postulated his theory, he was thinking of brittle solids. And that's partially true. So Griffith was actually interested in solving metal fatigue. So he was working at Rolls-Royce at the time, and he was interested in solving metal fatigue. But it's true that he formulated his theory in the context of an experiment that he did with glass. And this was easy for him because then, for the fracture energy, he didn't have to do a fracture experiment. There was no fracture mechanics theory back then, but he could relate this to the surface energy. What happens if you want to look at plasticity? Well, I mean, of course, thermodynamics also holds in the presence of plasticity, and Orowan in the 40s already said, Griffith's relationship holds for plasticity as well. It's just that, this fracture energy is not the surface energy of glass, or twice the surface energy of glass, as Griffith said, but it's a much larger quantity. That for steels could be 1,000 kilojoules per square meter. So that's one thing. But then there's another thing. So yeah, that's good. Of course, thermodynamics holds, the energy balance still holds. In principle, you can apply the method as it is to plasticity. But there's one additional aspect. So we said our driving force of fracture, before we were talking about the elastic strain energy density, is the energy stored in the material, right? That's what thermodynamics tells us. So it's the elastic strain energy density. So now what do we do in plasticity? Well, different people have taken different approaches. But what we believe is consistent with thermodynamics is to consider not only the elastic strain energy, but a small fraction of the plastic strain energy. And there were, I mean, it is well known since quite long ago, the first paper, I think, is with the seminal experiments by Taylor and Cooney. We know how much of plastic work gets dissipated into heat and how much is stored in the material. And under room temperature and standard loading conditions, this is typically 0.1. So we have a prefactor here, and this prefactor we take equal to 0.1 because we know that, and in all the results I'm going to show, we of course typically deal with elastoplastic materials. We're interested in steels. And in those cases, we have that the energy stored in the material is going to be the elastic energy and 10% of the plastic energy because we know that the rest is going to be dissipated as heat. So again, in agreement with the thermodynamics of fracture, but take into account that not all plastic work is stored in your material. And this is, I would say that one possible question is, how are you making sure that this is correct? I mean, the experiments of Taylor or Queenie are quite clear, but is there any way to double check that everything's going well? One way of double checking is, as I told you before, the length scale can be related to the strength. And this is an R curve, crack growth resistant curve. And you know that when you have a crack growth resistant curve, basically, this is in the absence of hydrogen, by the way. When you have a crack growth resistant curve, you know that basically if you had an ideally brittle material, you have a flat curve, a flat response. But when you have an elastoplastic material, you have plastic dissipation, and the plastic dissipation is what brings this kind of toughening, this rising R curve. So if you have correctly captured the role of plastic dissipation, your R curve should be the same as in the experiment, because this is the only contribution to the R curve, right? The plastic dissipation. If you're dealing with composites, maybe you have, other toughening mechanisms like fiber bridging, but if you're dealing with metals, it's just purely plastic dissipation. So a good way of checking if your model is able to capture plastic dissipation properly and fracture properly in elastoplastic solids is by looking at the R curve. Okay, so that's when it comes to fracture. Now, I think one of the potentials of facial fracture is that we can extend it to fatigue. And of course, in practical applications, most engineering components are undergoing cyclic load. So we need to account for fatigue. And this is a challenge for many other more complicated damage models because they don't really have the mechanisms of fatigue in it. But the good news is that, fatigue builds on our understanding of fracture mechanics. Our engineering standards for fatigue build on Paris law or on fracture toughness, on ideas based on fracture mechanics. So this seems like the natural extension for phase field. So this is the question that I showed you before. Okay, what do we do when we have fatigue? And what you do when you have fatigue is you define a fatigue degradation function, a fatigue degradation function that is basically a function of some variable alpha that accumulates with the loading cycle. So basically this fatigue function will reduce my fracture energy as I do more and more cycles. So it's a measure of how a material will be more susceptible to develop cyclic damage, basically. And basically, there are multiple phase field models that have been proposed to fatigue. The one that I like the most is the one by the group of Laura de Laurentiis at ETH. And in their simplest model, what they proposed was a model where basically it's okay, the variable that is accumulating must be the stored energy density because this is the thermodynamics. This is in agreement with the phase field model. But then we can make choices and we can define this fatigue degradation function and this parameter alpha zero. So you have a parameter that you need to fit to an experiment. That's the price to pay. But once you fit the parameter to an experiment, they have been able to show that you can capture naturally as an output of the model, not as an input. There's many models out there that take as input Paris law. This is what we use in standards. We grow our cracks based on Paris law. This model will tell you what is Paris law as a function of toughness, strength, and this additional parameter. So you can see here SN curves, and you can see here compact tension virtual experiments providing you with Paris law. So this is the model that we like the most. But I had a PhD student working on this, Alireza Golamar, who was funded by Vattenfall, so he was an industrially funded PhD student. And therefore, he always had this kind of industrial mindset of trying to replicate experiments, making sure that we don't stay in our academic ivory tower. So he realized that when he used this model, he was not able to capture very well the experiment. So he added a bit more flexibility to the model, and he added this additional coefficient to the model that is parameter n, that basically you can obtain directly from an SN curve or a Paris law behavior, because you can show analytically that under assumption of linear elastic behavior, there's a correlation between the slopes of SN curves and Paris law. So we have this additional parameter that allows us to capture any arbitrary slope of the SN curve. So we had to pay the cost of adding one more parameter to our model, but again, we only have two parameters to characterize the fatigue behavior, and we're able to predict any arbitrary slope of SN curve and Paris law. And we can go, because we know that analytically there's a relation between Paris law and SN curve, we can go from one to the other straight away, naturally with this model. And in fact, we can show this. This is, for example, experimental data for PMMA. We calibrate the model only with an S curve, and we're able to predict fatigue growth rates. We could have done it the other way around as well. I think that this is quite promising. For metals, it's a bit more complicated, right? Don't get me wrong. But I think it's quite promising that you have a tool that, you give an S curve and you're able to capture Paris law behavior. And this is very good news as well, because it's similar to what I said before about fracture. S curve and Paris law provide the two extremes. S curve is when you have a smooth sample, no cracks. Paris law, you have a big crack and you're more than fatigue. So if you're able to capture both extremes, it means that no matter anything that you face in between, you're gonna be able to capture well. And you can see that the model is able to capture here S curves for our material, for different load ratios. Very good predictions, even the endurance limit. And here, this is the famous Kitawa-Takasaki diagram, KT diagram, where similar to what I showed you before. This is failure stress versus crack size. And you can see that, of course, we produce the static case, and then we can produce these KT diagrams for any arbitrary choice of cycles. So again, this is what we use in our engineering standards, and this comes naturally out of our model. And we can see that we can get the two extremes again, so the endurance, the infinite life, and the static life, and we can get what is in between. Sorry. So again, quite exciting, because not only we're in agreement with well-established fracture mechanics theory, but we're also in agreement with well-established fatigue theory. Okay, so let me summarize. Why is facial fracture and fatigue predictions, why are they physically sound? Multiple reasons. One is that you predict cracking when the energy release rate reaches a critical value, or when your stress intensity factor reaches your material toughness, in agreement with thermodynamics and well-established fracture mechanics theory. So this is good. So not only, it coincides with what we have been working on for the past 50 years, but it's also in agreement with what engineers know, what we have in our engineering standards. So for the simple cases where you can apply, analytical fracture mechanics, the model will give you the same result. But you can also use the model to tackle more complicated cases, which you cannot tackle with the standards. For example, when you bring hydrogen into the picture. It also incorporates the concept of strength, fracture stress, and therefore it can capture the transition flow size effect. So you can go from toughness-driven failures to strength failures for both fracture and fatigue. So this is the so famous KT diagram. And this is again quite good, because it means that if I can deal with samples with tiny cracks and with very large cracks, it means that no matter what your crack size is, I'm going to get the same result as in an experiment. I think that the model is very promising as well in fatigue, because you can naturally capture Paris law and S curve behavior as an output of the model, not as an input. And you can capture as well naturally the transition from one to the other, as you can show analytically, and the model is able to recover that. So if you get an S curve, you will be able to predict fatigue growth behavior. And then I must emphasize, the model takes as input only two parameters with a clear physical meaning: the strength of the material and the toughness. So if you're dealing with an elastic material and you more than fracture, then you have Young's modulus, Poisson ratio, toughness, and strength. If you're dealing with an elastoplastic material, a metal, and you're dealing with fracture, you have Young's modulus, Poisson ratio, yield stress, basically the stress-strain behavior, characterized typically by yield stress and a strain hardening exponent, and then again fracture and strength. And the most complete case is one where you're dealing with an elastoplastic material and fatigue, and then you have Young's modulus, Poisson ratio, yield stress, strain hardening exponent, and then the two fracture properties and the two parameters that we use for the fatigue predictions. So I think this is quite important, because it's easy to fit things a posteriori, and when you have tens of parameters, but fitting things with parameters that you know in advance and fitting things blindly, as we showed you before, I think that's a different story. And this is what gives me confidence in this kind of model. Okay, so let me move to the next step. Why are phasing models so numerically robust? Why are they so popular in the community? Let me provide some details of the numerical implementation. So I think the key approach is that basically the key reason why these are different to other models that I just showed before. Because, for example, I was talking before about these ideas of fracture energy and strength. Those ideas are also inbuilt in cohesive sum models. So in a way, it's not that different. Of course, different to cohesive sum models, this allows you to predict cracking in an arbitrary way. So you don't need to know in advance where your crack is going to grow. But also, it seems that the method is very robust, because, as you know, predicting the damage of materials is complicated. Some people even need to go to explicit schemes because they don't get convergence, because suddenly you have a sudden loss of load carrying capacity. So your Newton-Raphson algorithm struggles to converge. But it seems that phase field doesn't suffer from those problems. And there's a lot of applied mathematicians working on understanding why this is the case. To put it simple, the idea is that you are uncoupling your damage from your mechanical problem. And this sort of uncoupling gives you some additional robustness. So you can see, you have two equations to solve, the one that you normally solve and an additional one. So there's, as you can imagine, two typical approaches that you could use to solve this problem. One is a monolithic approach. This is the way we will solve our quizy cell models, for example. So basically, you solve both equations at the same time. And this is good because it means that it's unconditionally stable, which means that no matter how big your time increment is, your results are going to be the good ones. However, similar to any other damage mechanics problem, it's complicated to get convergence often with this. I have a student of mine that really likes this approach, and he uses it, and he claims that he can get convergence, but it takes some time and it's complicated, similar to any other damage model. What people have noticed in the phase field community is that you can use a stagger approach where you solve them sequentially. So first you solve this solution, you get a displacement solution, you calculate the strains, you go in here, you calculate the phase field, then you go here, and so on and so forth. So you solve one and then the other. And then what the applied mathematics community have shown is that for a fixed displacement field, the functional is convex with respect to the phase field and vice versa. So the method is very, very robust in that you get convergence. However, what we believe is that the best approach to take here is to combine monolithic approaches and quasi-Newton. So these are methods like the so-called BFGS solution scheme. And when you combine these two, so this is fine, and this is what most people do, and this is fine, but I believe that this is the best approach. And when we combine these two, we get a solution that is unconditionally stable. We can use very large time increments and is very robust. Let me show you some examples. So this is a classic benchmark in the phase field community. What you have here is essentially a square plate with a crack subjected to uniaxial tension. This is a linear elastic material, so this is mode 1 fracture. The crack is going to propagate in an unstable manner. So from one moment to the other, we're going to have a full cracking event. And here on the right, what you can see in red is the force displacement curve. So you can see that the load increases, and then at some point you get this unstable cracking event, and boom, you get this massive load current, loss of load current capacity. And as you can imagine, for a solution scheme, it's very complicated to go to this point because it's a big jump. However, phase field is able to do it in any approach that you use, monolithic or stagger. But with this monolithic quasi-Newton, we're able to do it pretty quick. So what you see on blue is on the y-axis the number of iterations per increment, and these bars denote each of the increments. So I've used 30 load increments here, but actually you can solve this problem with as little as 10 increments. So you only need 10 increments to solve an unstable crack growth problem. And this basically means that you can run this over a few minutes in your laptop. And this is a comparison with stagger schemes. Stagger schemes work very well, but you need to, particularly if they're single pass, you need to use smaller time increments. We have shown that our results are a bit more robust, but this is more for the people working in this area. So let me say a few words about implementation details. How different it is, those models, from my standard finite element code that I use in ANSYS or Abacus and so on. It is pretty similar. The only thing that you need to solve is an additional degree of freedom. So you need, in addition to the displacement, you solve for the phase field. So it's an additional equation. But this is actually straightforward to implement. The first time I heard about phase field was in 2016, and I went back home and I implemented in the morning afterwards. So it was really straightforward. But let me show you one way where you can do it even more easily. So you can see here that this equation can be easily rewritten as this. It's the same thing. I'm just moving things around. And then if I look at the equation for heat transfer under the steady state with a source term, you can see that it's very similar to what we have here. So I can find an analogy. I can think, okay, what if temperature is phase field? I define the thermal conductivity equal to 1, and I define the source term as this. If I can do that, any finite element code that can run thermomechanical analysis, which are all, you can use the thermomechanical analysis as factor. So you can assume that the temperature is the phase field, and therefore you can run analysis. And this, in the context of Abacus, for example, is straightforward because you implement this at the integration point level through a UMAT or UMAT and headball, and you're able to, basically you need a UMAT to define this guy, but it's all at the integration point level. So it's the same equation basically as the heat transfer equation, so you can do an analogy, and therefore without making big changes into your finite element code, you can run this straightforwardly. This code, we have provided all our codes, and this code is, I think, 20 lines long, so it's a very short code. One problem, of course, comes with fatigue when it comes to the numerics. Fatigue, one key aspect of our fatigue analysis is that we do cycle by cycle calculations. And this is very powerful because it means that you don't need to, you can give me any arbitrary loading history. You can say, my pipeline or my pressure vessel are going to be subjected to this arbitrary loading history and different load ratios, different frequencies. Could you please put this into your model and tell me what's coming out of this? And normally what engineers do is they apply some sort of superposition, but superposition doesn't apply with hydrogen because we have, hydrogen diffusion. So what do we do there? We need to look at cycle by cycle calculations. But this means that if you're dealing with a component that fails after millions of cycles, which can happen, then you're going to have to do millions of cycles in your computer, and this can be quite heavy. So for that, we have been working on acceleration schemes. One was this quasi-Newton approach that I showed you before. It really delivers very impressive predictions. We also work on some constant accumulation schemes, taking advantage of the fact that cracks will only grow under the tensile part of the loading cycle. And also you can use what people call cycle jump. So if your component is going to fail after 20 million cycles, then maybe cycle number 53 is not that different from cycle number 54. So you can assume that cycles from 50 to 60, they all behave the same, and then in cycle 60, you do another calculation. So that's one approach. And then we also use this kind of modified Newton approaches, taking advantage of the fact that you don't need to build the stiffness matrix on every calculation. But anyway, that's more for the experts. Let me just give you an overview, because now when you take account all these considerations, as you can see here, this is a simple test that we did where we have a kind of uniaxial tension, but with a tilted crack. So you expect some sort of funny crack behavior. This is the detail of the finite element mesh. As I told you, we need to resolve the length scale, and we don't know where the crack is going to be. So we're going to refine the entire thing. And you can see that we can predict, so it's a very fine mesh. It has 3 million of degrees of freedom. This is 3D. And you can see that we do 600,000 cycles. And nowadays we're able to do millions of cycles in 3D. And basically you see that by the way that we're using a direct solver, and we're considering, we're only jumping every 4 cycles, which is quite conservative, taking into account that it fails after 600,000 cycles. So again, these things are computationally heavy, but we have developed schemes that can handle these things. And we are at a point where we can do full 3D calculations over millions of cycles. So I think there's very few engineering problems that are out of our grasp. Okay, so now comes the hydrogen. What do we do for the hydrogen? Well, there's many things we could do. And I've been working on this area for quite a while, so we've done quite a lot of modeling on the hydrogen uptake, both from electrochemical and gaseous environments, for the hydrogen transport with multi-trap models based on Oriani, Magna Foster. But I'm not going to focus on those aspects here. I'm going to assume that I know what is my hydrogen concentration at the surface of my metal. I have any hydrogen transport equation that you wish. This is the simplest one could use, right? An extended version of fixed law, but you could include traps, include whatever you feel. And now I'm going to focus, of course, on the damage process. How does hydrogen influence the damage process? Quantitatively, we know what happens. Hydrogen reduces the fracture resistance of metals. So we must make our fracture energy dependent on the hydrogen concentration, or come up with a hydrogen degradation function. And we have followed 2 approaches. I think initially we started with a mechanistic approach. We said, if we look at this problem across the scales, if we do DFT calculations, these were done, by the way, these are DFT calculations for 2 types of grain boundaries in nickel. These were done at Sintave by Antonio, Bigdis, and co-workers. And you can see here that what they predict is that if your coverage, for example, the occupancy of your grain boundaries is quite high, then you get a very significant reduction in fracture toughness. So since we are solving for this hydrogen transport equation, you can use Oriani's equilibrium to find what is the coverage of your critical interface, like a grain boundary, and then you come in here, and you reduce your fracture energy in agreement with this. So this model requires no parameters whatsoever, just a DFT calculation offline. So it's kind of a mechanistic approach. And the other approach that we followed was a phenomenological one. So a lot of our industrial partners said, atomistic calculations are a bit obscure to us. We don't really know what's happening in there. We are working with materials that we understand very well, pipeline steels, pressure vessel steels. These are data for pipeline steels, by the way. We have toughness or fracture energy data versus hydrogen concentration. Why do you just feed the data and input that into your model? And you can do that, and then you have a facial damage model that is in agreement with experiments. And as long as you have experimental data across, from no hydrogen to fully saturated with hydrogen, you will be fine. Okay, so one last thing before I show results. So another thing that you need to take into account is that, of course, as your crack propagates, if you are exposing your component to a hydrogen-containing environment, you need to be able to capture the fact that your hydrogen-containing environment is going to quickly follow your crack, right? So if you have a pipeline exposed to hydrogen gas, the moment the inside crack grows, the hydrogen gas is going to be exposed to that, is going to be in contact with this new created crack surface. And that in this kind of facial models is really straightforward to incorporate, because the facial is a marker. So it's telling you where your crack lies. You can see it here, the facial growing in the top, and then using a penalty condition, or you can use an enhanced diffusivity, you can capture how, as the crack propagates, your hydrogen concentration from the environment immediately follows. Okay, let me move to the third part. I think I'm well on time, showing some representative results and benchmarking against laboratory experiments. So these are some representative results. For example, these are pre-charged steel bars. You can see here, these were some high-strength steel bars that were immersed into hydrogen gas, and then they measure the various hydrogen concentrations, and they measure the notch tensile strength versus the hydrogen content, and you can see that we got a very good agreement with the model. These symbols are the experiments. The model is the black line. And again, this has no fitting whatsoever. Quite a good agreement. These were a set of experiments conducted at SINTEF, where they were looking at duplex stainless steels. I think Bigdis was quite involved in this. So they immersed these duplex stainless steels into a seawater bath. They applied different loads, and they measured the time to failure. And you can see that one of the benefits of the model is that not only you can reproduce experiment, which gives you confidence, but you can also run virtual experiments over very large time scales. And therefore, you can determine what is this critical threshold below which embrittlement will not occur. And basically, you can model anything. So these methods, are finite element methods, so you can incorporate them with many other possibilities. So one situation that we look into is, the failure of metals in corrosive environments due to hydrogen. And that's a much more complicated scenario than gas, because you have basically a crack or a defect. That crack of defect is, depending on the shape and the geometry of the crack defect, you can have very different electrochemistry. So the electrochemistry, you can see it here, right? This is the electrolyte potential and the pH. It varies quite dramatically to inside of the crack to outside, where you normally do your measurements. And this is quite important, because if you are thinking of establishing a connection between, permeation, electrochemical permeation, and gaseous systems, you don't have those changes in electrochemical potential. It's a completely different scenario to a fracture process. The moment you have an occluded electrochemistry like a pit, you need to be able to capture how the electrochemistry changes within your defect. But you can do that with finite elements, and then you can simulate also the surface reactions, and we have a method for predicting the fracture opening, but that's another story. What I want to say is that no matter what complex the problem is, you can combine these methods with other more complicated scenarios. So I was showing you the most simple scenario, but if you have a robust model to handle hydrogen uptake and so on, you can combine that easily with this model. And basically, you can solve anything you want. So this is a classic standardized test. As you know, screws and bolts, they suffer a lot from hydrogen embrittlement, as they're high-strength materials. So this is a classic test where you have a metallic screw inside of a concrete material. You can simulate the contact of the two materials, and you can see the full fracture of the screw. You can go also down the scales. So nowadays, there's a lot of interest in predicting nucleation of fatigue cracks, which could be more microstructurally dominated. So you can use these kind of facial models together with crystal plasticity, with EBSD images of your microstructure. And as you can see here, you can predict how cracks develop in your microstructure. But also you can go up the scale. So you can handle, these are continuum level finite element models. So you can handle, and computers are big enough these days. So you can handle pipelines, you can handle pressure vessels, any geometry that you are interested in. So you can finally bring this idea of virtual testing that has saved billions to the automotive and aeronautical industries to hydrogen containing environments. And I think quite excitingly, because the model can not only deal with cracks, but with defects of any arbitrary shape, we can eliminate conservatism, and we can basically deliver predictions for problems of arbitrary complexity. So what you're seeing here is a pipeline. This is from British Petroleum, BP. This pipeline contains many, many defects due to pitting corrosion. All those red dots are defects. We model a critical section of 3 meters of that pipeline that contain more than 100 of those defects. And because I'm solving for the facial as a degree of freedom, I don't need to change my mesh to make a complicated mesh to accommodate those defects. I can have the same uniform mesh for all my pipelines. So for engineering purpose, this is quite powerful. And then we start loading our pipeline to in-service conditions. And then as you can see here at the top, those defects start growing. Eventually they start merging. And eventually you get the complete failure of the pipeline. I need to say that this looks a little bit like a video game, but as you can see, this is a fully mechanistic prediction. So at the end of the day, we have a tool that allows us to predict how failures will develop in hydrogen-containing environments as a function of the material, the loading conditions, and the environment. And as you can see, what is an important takeaway, I think, for this meeting is that the model is not only able to handle simple academic problems, but is also able to handle problems of arbitrary complexity, the scales and complexity that are inherent to engineering practice. So let me get into the fatigue part. So again, I showed you before that phase field can be used to model fatigue. So why don't we combine this with hydrogen? And one thing that I'm going to emphasize, we do not come up with additional parameters. We do not couple the fatigue process and the hydrogen process. The way we couple them is that we say, my fracture energy is going to be dependent on this accumulation history variable, and also the energy accumulated through the number of cycles, and my hydrogen concentration. And you can see then we can use the model to predict virtual SN curves with and without hydrogen, showing what I believe is a good agreement with experiments. The model can also be used to predict as an output of the model Paris law behavior for different hydrogen concentrations. And virtual SN curves for any arbitrary choice of geometry. This is a notch sample, environment, and loading history. And we recently used this. I'm not going to spend time on this because the focus is not today pressure vessels or fatigue, but we recently used this in collaboration with our colleagues from Tenaris to understand the failure of pressure vessel steels. So basically, they provided us with data in air. So this was the piece of data in air. So we calibrated. I remind you that the model has basically Young's the stress strain behavior of material, Young's modulus, Poisson ratio, yield stress, strain hardening exponent. Then you have the fracture behavior, so strength and toughness, and how the toughness degrades with hydrogen content, and then 2 parameters to characterize the fatigue behavior. So we calibrated those 2 parameters with a curve in air. This is in the absence of hydrogen. And then they have Sandia data for different loads, different hydrogen pressures, different frequencies. And we basically changed the boundary conditions in our model without touching any of the parameters of the model. And as you can see, our predictions seem to be in very good agreement with all those data. Again, we didn't touch anything of the model. We just changed the boundary conditions. We load with a different load ratio. We apply a different hydrogen concentration at the surface because we changed the hydrogen pressure using Siebert's law. So there was no fitting any recalibration. It's the same model. We just tell the model that we have a different scenario. We have hydrogen, we have different loading conditions, and it gives us a very good agreement. And now, of course, because these models can be used not only to reproduce fatigue growth in lab samples, we're also using these models to predict the evolution of the failure of pressure vessels. And we seem to be getting a good agreement with real scale pressure vessel testing. Okay, that takes me to the very last part of my talk, and I think that I'm doing well on time. This is related to pipelines, which is a thing of interest here. And you all know that the question, so the key question is, okay, how do we make Can we transport hydrogen through existing natural gas pipelines? And as I said, this is a very difficult question to answer experimentally. First of all, because the weakest link is going to be the wells, and it's very difficult to extract relevant material samples from heat-affected zones. Wells have residual stresses. Again, very difficult to account for residual stresses in our lab. And it's also even difficult to account for these things at the large scale, real scale examples, because you have an oxide layer that you need to disrupt. And so it's quite complicated. Not only is it expensive, of course, to test a full-scale pipe, but it's also quite complicated. So I think that models can give us good insight. Also, of course, because we have so many conditions, right? We have thousands of kilometers of those pipes with different steel grades, different types of welds. So it's very difficult to test all of those scenarios in models in the lab. But models can test those scenarios quickly and tell us what is the worst critical scenario. So what do? We basically have the same models that I showed you before. So those couple deformation, diffusion, fracture models. And then what we do is we simulate also the welding process to get the residual stress distribution. But before I get into that, I mentioned before, we need to make sure that the model is predicting what we expect. And I mentioned before, we need to capture everything, the plastic dissipation, the embrittlement, and so on. So we ran first some virtual R curves and compare them with experiments. You can see this is for an X80, this is for an X52, and you can see that we get a good agreement in air and in hydrogen content. And there's some details here, but I'm going to skip those. We can talk about them in the Q&A session. And yeah, this is the response in air in hydrogen, so everything is looking quite good. We are quite confident that the model is able to capture very well, how embrittlement affects these materials, what degree of plastic dissipation. So this is basically a model that is in agreement with well-established fracture mechanics, but it's also able to model hydrogen transport. It's also able to model a situation where you don't have an homogeneous material. Because, of course, fracture mechanics works well, and at some point you say, Emilio, why don't I just use fracture mechanics to design my pipes? Well, the problem is that fracture mechanics works for an homogeneous material. But here you don't have an homogeneous material because you have a hydrogen distribution within your pipe, and this is making your toughness dependent on the hydrogen concentration. So you need something more sophisticated than fracture mechanics. And this model works well with fracture mechanics for homogeneous materials, and therefore it should work well for cases where you have hydrogen transport. So first we do the welding process modeling. This is a sim weld, so it has 2 passes, and there's multiple ways you could do welding process modeling. There's an entire community dedicated to this, and we're now actually working with more sophisticated methods just to see whether we can get a more precise description of microstructure and residual stresses. But once you get basically your residual stresses, then you run your simulations in the presence of hydrogen. So what we do is we expose these pipelines to a rising hydrogen pressure until we see failure. You can see here, this is the hydrogen content. As you can see, it's growing with the hydrogen concentration as we increase our pressure, and also it's changing due to diffusion. You get this kind of a steady state profile. And this is, as I said, important because, again, we cannot use fracture mechanics for this because you get a very different stress toughness distribution, right? So the toughness here is going to be the one in air, but the toughness in this red area is going to be the one severely degraded by hydrogen. But basically what we do is we increase the pressure, and then we see how failure happens. And failure can happen one of 2 ways. It could be that your entire pipeline will collapse due to plastic collapse, so you have plasticity all over the place. The other option is what you see here. Eventually, you trigger a crack. So we consider one case as plastic collapse, and if plastic collapse happens before cracking, that's the end of the calculation. We say, this is a too high pressure. They're not going to use this in practical applications. But if cracking happens before plastic collapse, we say, oh, careful. Engineers probably did not design pipes for this scenario. And then we use the model to learn things. One thing we wanted to learn was whether residual stresses matter or not. And we saw for I think it was for the X80, that without residual stresses, we get this kind of plastic collapse mechanism where we don't get cracks propagating, but when we reach a sufficiently high pressure, the entire pipe gels. But when we have residual stresses, we see that actually below the plastic collapse mechanism, we have a crack propagating. So residual stresses do matter, and that makes things complicated. We also worried about weld-induced porosity. So we introduced some random porosity for volume fractions of microvoids that are typical for welds. And there we saw a small effect, but not a big effect. So we thought, welding-induced porosity might play a secondary role. Of course, what we expected is that pre-existing defects will play a major role, and they did. So we tried to do a systematic study on the type of defect, their orientation, how these play a role. I'm not going to get into details here, but I would say that the one critical scenario that we observe where we obtain the lowest critical pressure is when you have a defect that is roughly 3 meters long along the heat-affected zone. And this is important, of course, because 50 megapascals is one of the pressures that has been discussed to transport hydrogen in natural gas pipelines. But also it's important because we know from pipes taken out of service that it's not impossible to have a 3 millimeter crack along the heat-affected zone. So this is not an unrealistic scenario. And we published this paper back in December last year, and I was told relatively recently that some large-scale experiments took place I think it was in February, somewhere in Europe, and they introduced with EDM an arch in the weld, and they saw a critical pressure of failure of 12 megapascals. So it was interesting to see, I don't know all the details, but it was interesting to see that the model predicted something that was very close to these large-scale experiments before these experiments happened. And we also worried about microstructural heterogeneity. So one way you can incorporate that is by doing harness maps. This is work together with EPRI, I should say. So we implemented those harness maps into our model, and then we were able to predict the propagation of cracks and so on. And we saw that the microstructure matters, but there's still a lot to be said in this area. Okay, so that's all. Hopefully with some time for questions. I'll just say some few concluding remarks. I hope I went slowly through the concepts, so the basic concepts underlying phase field theory, and that you're all more familiar with the idea now. What I believe is that the combination of phase field and this kind of multi-physics modeling, where we can simulate the equations that describe hydrogen uptake, hydrogen transport, will allow us to develop a mechanistic computational framework that resolves the physical processes underlying hydrogen embrittlement. I think one key point is that this method is, as I said, in well agreement with fracture mechanics, which means that we can use it in situations where fracture mechanics applies. But the problem with hydrogen is that it's difficult to apply fracture mechanics. You can apply it to a certain extent, but you don't have any more an homogeneous material. So you can apply the fracture mechanics concepts, but in another more rich scenario. And I think this platform provides a richer scenario. And now the same goes for fatigue, right? You have fatigue frequency effects. You cannot anymore apply superposition. So time matters. So these kind of things make it more complicated. But if you have a method that is in good agreement with fracture and fatigue theory, then and is able to predict the transport of hydrogen precisely, which you can do because it depends only on a diffusion coefficient that you can measure in your lab, then you're able to capture this interplay between hydrogen transport, fracture, and fatigue. I think the good news is that the framework is very general. I've seen many other groups using this framework to develop new mechanistic hydrogen degradation functions based on their observations and their beliefs. And you can also combine this very easily with other work that has been going on in the finite element community, right? So people working modeling macrostructures, crystal plasticity, you can combine this with crystal plasticity, weld process simulations, you can do that, stress corrosion cracking, and so on and so forth. I think the one key aspect is that the framework is very robust. It takes only 2 parameters as input, fracture, toughness, and strength. And it seems to deliver a very good agreement with experiments. But not only laboratory experiments, but also large-scale, real-scale virtual testing of components. Well, we have seen that when we compare them with experiments on pipes and pressure vessels, we seem to be getting a good agreement. Not only you are able to handle this, but you are able to handle this with good precision. And 2 examples that I always like to show, that I showed briefly the first one today and a bit more in detail the second one, is that you can use these models to replace those very expensive fatigue crack growth experiments where you need to run a crack over hundreds of megapascals, or at least 100 megapascal of hydrogen pressure. And then you can also use it to determine what is the maximum admissible pressure in hydrogen transport pipelines. And there are any variety of scenarios that you might consider of residual stresses, defects, types of wells, and so on and so forth. So that's all. As you know, or some of you know, we release all our codes, so you can download them all from our website. Most of the results today have been computed using Abacus routines. I also show some COMSOL results and some results for in-house codes that we develop in C++, Julia, or MATLAB, also using sometimes open source projects like Phoenix. As you say, COMSOL is catching up quickly on this front. They have facial fracture already implemented, and I believe Abacus is also working on that. So they have already a sim built, so you don't need to be a finite element expert. You click a button, and facial fracture is already part of your portfolio. And COMSOL has also implemented, based on our recent models, some more sophisticated hydrogen uptake and trapping distribution models.